All right, welcome back to the SciMax channel on electronic lab notebooks. Today I want to talk about design of experiments and active learning and surrogate models for the self-driving light demo. So the idea here is that we often will take our data and fit a model to it. We're going to call that a surrogate model. That means it's a model that acts as a surrogate for the real experiment, and we use it to make predictions or optimize or something like that. And we're going to look at two styles of doing this. One style is the design of experiments, and there we typically will fit a polynomial surface to the data. That's a linear regression. That means we need all the experimental data up front so that we can do the regression. And if you need a lot of experiments, then it's expensive and you kind of don't know anything that's happening until basically until the end. There are other kinds of models, though, like machine learning models, a Gaussian process model in particular, where you can get by with less data, at least to start with, and you can make predictions with only a few data points. Now, they may not be great predictions, and you can't extrapolate to the entire space, but you can use a local region of data to figure out where the next experiment to go is, and we call that active learning. Sometimes, if the model is very good, if it's the right kind of model that fits the data really well, then you can get quite far, and you may be able to do fewer experiments by active learning than by a design of experiments. But there's trade-offs, because with the Gaussian process model, you can't say with much reliability what happens outside your data space, and there's hardly anything to interpret. Whereas the design of experiment, you are able to interpret coefficients as how significant a parameter is, like if there are interactions and things like that. So it's a little bit of a trade-off of what's important, and is it important to make some insights into importance of parameters and interactions, or is it more important to do as few experiments as possible to get to an answer that you can see is reasonable? Okay, so let's go ahead and get started. This code is old. You've seen it a couple of times in the self-driving lab demo. This is getting code from the Python package for the self-driving lab demo, and it simply creates a get results function that will get all the results for a particular RGB value and a label. So that part's not new. What is new is that we're going to couple this now with a surrogate model, and not the same way I did before, but we're going to create a new sklearn compatible estimator, and I'm going to call it LR for linear regression. And what we need for a surrogate model is to know when can I trust the surrogate and when should I run an actual experiment. And we're going to trust our surrogate when the prediction error is sufficiently small. And then if it's not, we're going to use the real data. So this model has a capability for that. We use the regress and predict functions from pyxy, and those provide uncertainty estimates on the parameters and predictions. And so we'll be able to set a tolerance then. If the predicted error is less than the tolerance, we'll say it's reliable, and if it's greater than the tolerance, then we'll say it's unreliable. And in this case, we know that the dependence on RG and B is like order 200. That's the order of the coefficients in the linear model. So we can say, anything, if the predicted error is less than, say, about 50, then it's as good as we were going to measure more or less anyway, and we might use that. You have to choose this tolerance, and we'll come back to it in a little bit. But otherwise, we just define a linear regression class here with a fit and a predict function, and then I wrap that in a pipeline so that we can have an RGB value get converted into second-order polynomial features. Then those second-order polynomial features get passed into our linear regressor in a convenient way. Okay, the next most important block is this new idea of a surrogate. And so the surrogate here is a decorator. And what we do with the decorator is a function that takes a function and returns a new function. And surrogate is actually a class here with a call method, but we define our surrogate model and a tolerance. and I picked 100 here because that's about half the distance between adjacent RGB measurements. So what we're going to do here is when we call measure, it will check the surrogate and see if it can make a prediction. And if it can, it will get the errors. And if the errors are less than this tolerance, we use the surrogate model instead. And if the errors are larger than the tolerance, then we run the actual measure function and then retrain the surrogate. And this way we will iteratively build up our surrogate model as we make measurements. Now the fitting is going to require at least 10 measurements because there are at least 10 parameters in the model. And so the first thing we have to do is initialize it. Now you could initialize with the design of experiment approach we did before, but I'm going to initialize here with just 12 random samples from 25 to 75. And this takes whatever 12 times 7 seconds to run is. And so we'll have to wait here about a minute. Maybe some of these have been cached, and so it's picking them again. Okay, so now we have initialized our model, and we're going to go ahead and try an optimization. So I'm going to stick with the previous goal of how do I get an RGB value to get 10,000, 10,000, 10,000. And so here I set up an objective. Here we make a measurement. I make sure it's at least 2D and that it's also an integer. I subtract 10,000 from all of them, and then we're going to minimize the summed absolute value of those. All right, and now when I run this, this is going to, every time it makes a guess, it's going to run an iteration. And eventually it's going to finish. It takes a handful of operations here. Okay, so that ran and it found a solution around 43, 59, 36, which we saw before. And we can see what that comes out as. These are all quite close to 10,000 as expected. And we can see what the uncertainty on these are by looking at what comes out here. And so the uncertainties are, in the range of 57 to 30, which are bigger than the normal measurement ranges that could be a feature of the tolerance that I set, that it should have run more. But let's have a look at, let me get rid of this report. Here, what we can find here is that we have used 20 data points and the model was fitted 9 times, but the surrogate was used 110 times. So if we had naively used the measure function without the surrogate, we would have had to make 110 measurements, and we instead only had to make 20 measurements here. And 12 of those were what we started with. Now I like to see how things look. This is the parity plot of our model, and the R² values between these are quite high. So our model is actually very good, and we knew that before because we knew that a quadratic surface fit the data pretty well. All right, we can do other models, right? So that previous one I had to initialize with 12 data points just to get a reasonable starting fit, and then we had to update the model as it goes. We can try something different. So here I'm going to try a Gaussian process surrogate. I'm going to restart here just to get everything fresh. and talk about the Gaussian process kernel that I want to use. So the kernel that I want to use is the dot product, and that's the same as a linear kernel in sklearn. And I want to use a linear kernel because we're going to generate polynomial features again, and I know the output is linear in those. And so you should use a kernel that represents the dependency that you know to exist already. And then I'm going to put a white kernel on top of that because I know there's some noise. When we've made measurements, we see noise that is in the, like, I don't know, 10 to 20 range. Maybe we can make this more like 5 to 20. So I know there's noise in there, and I don't want it to overfit. So we're going to include this in the kernel and then make a Gaussian process regressor. And then I'm similarly going to use the polynomial features, so that we'll take RGB to those polynomial features and then basically do linear regression by Gaussian process for that. And then we'll make a new surrogate model here. Now, it's always a good idea to initialize the model. Here I'm going to initialize at this low corner, the high corner, and then like 2 of the faces. Maybe we could do, why don't we do the other 75, 25, 75, like that. And I guess this one is at 25. So that gives us like 5 points that we can run. So this is now the first time we've run it, so it's running this to initialize it, and that just gives the model some data points to work with. And we know that it's linear, so we should be able to interpolate things quite reasonably. And here I use a similar objective, so we're going to look at the sum of the absolute value of the result minus 10,000. So let's wait for these 5 to finish. Okay, and it looks like we've got some small numbers, some big numbers, and 10,000 is in that mix. All right, now I'm going to try a different optimizer here. I'm going to try the brute global optimization algorithm. And we're going to still search in this range of 25 to 75, which is what I know, where I believe the answer to be. And let's see, let me look at the surrogate up here. I set verbose equal to true on this one, so we'll be able to see a little bit better what happens. So I'm going to run this, and we're going to see some output. And so what this does is it shows me the input that we're running. This is the predicted output, and these are the errors that it's predicting. And these are greater than 50, the tolerance I set for this one. And so this is just kind of running along and giving us some verbose output, and eventually this one's just going to print the solution. Brute doesn't show you the whole solution structure. And it's a little bit baffling to me why the errors seem to stay so close to the tolerance that I set. Oh, here it is. It looks like this is the answer that it's found. And we can look at the plot here as well. So this one doesn't have so many data points. And here we were able to find a solution in only 10 data points. So that's much less than the standard design of experiment that took 20, and less than the previous one that we did. But look how many times we ran the surrogate, 8,000 times. If we had very naively tried the brute force algorithm here, it would have been over 8,000 measurements, and that is a lot of measurements. And the reason we only had to run the function a few times is because we had this surrogate model that was kind of built in. You just look at the pyroxy code. Just to give you a kind of a quick idea, the structure is very straightforward. The class is surrogate. You give it a function, the model, the tolerance, and then we save all these attributes. When you try to call it itself, what we do is try to call the model, and if you haven't fitted the model, you'll get an error, and that we'll handle that in the exception. And then we check if everything is less than the tolerance, and if it is, we return the proxy function. And if it's not, we run the actual function, add it to the training data, refit, and return the true values. And then if it's not fitted, we just run it like that. And then I added some convenience functions here to make that parity plot and to print the representation of the string. And then finally, there's an actual function. This is a little bit wonky setup in my mind, but one that is required. If you want a class decorator with optional arguments, then you need this helper function that allows you to construct the class. It's not super interesting, but this is what happens. All right, so we could do solution.asType int. That is 49, 60, 40, and if I do measure, maybe this needs to be in a list. I forgot. It looks like it. Then we get numbers that again are quite close to 10,000, and we can see that these are basically the same, I think. They are the same, so we're actually getting the model prediction, not an actual measurement. And we can say return std equals true, and see that the uncertainties here are quite low, 10, 10, 10 for each one, which is pretty helpful. So we don't really expect to see much happening in the uncertainty. We'll get some. We'd expect some number that is actually around that. Does raise an interesting question. What happens now if you want an actual measurement, not the surrogate? You probably have to do some fancy, clever use of the unwrapped version. So there is yeah, okay. We stored the actual function in func. So I could say measure.func, and this takes about 7 seconds, and then it'll do an actual run. No, that's interesting. This is not all that close to it. Oh, so we have to like trust but verify here. Oh, that's super interesting. It's like our surrogate model is overconfident, and there's not a super clear way for me to fix that. So that seems like something that ought to be added to the surrogate, because it has gotten itself overconfident in what the errors are, and so it's not actually giving true values. This is going to be a general challenge with any surrogate model approach. You never know without checking if the surrogate is going to be accurate or not. In this case, it seems like the surrogate is overconfident. It says that the surrogate thinks it's 9862, like plus or minus 20, but a true value is very far from that. So that is a feature of surrogates that you have to come around to understand, that without running the true function, you never know. And one way you could approach this is that you always check the final answer with the true function to make sure that it's correct. Or, as I alluded here, you could add some random checks, like 1 out of X runs you double check. But you'll have to think about doing something like that if you're going to rely on active learning and surrogate models. I'll also point out I'm not going to do it here, but I think if you used other kinds of Gaussian process, you would not get this fast of a result. So we're using a dot product. If you use the RBF kernel, I don't think it would be as accurate. It would take a lot more data to map out the space than we've had. So I'm totally taking advantage of some knowledge that we have a linear model in the polynomial space, and that's a much more powerful model for this data than a radial basis function. All right, I think I'm going to leave this one up because even though this isn't what I hoped would come out, this is what the surrogate model thinks is the most accurate lowest loss function, but it turns out that the surrogate model in this case is overconfident. And so I think what would have to happen here is we would have to add a way to add training data. So I have to add a new function to the surrogate class that will add training data, and then you would have to retrain it and then run this optimization again. And I feel pretty confident that would be a good solution, and also what you would normally do when you discover such a thing. So here you would see, that this output result here is not sufficiently accurate, and so we would want to add this point back and then rerun this optimization. And then you would do that until it converges. All right, that's it for today. Hope you learned something new about surrogates, and looks like we still have some work to do in how to update this so that we can avoid being overconfident. Thanks for coming.